hi everyone, we're about to get started. So my name's Jack.
I'm Evelyn.
I'm Carmania.
I'm Will.
I'm Isabella.
And this is our low-cost capacitive 6-axis four-stroke sensor. So just to begin, what is a four-stroke sensor? As we've come to know in this class, it's a sensor that captures both linear forces and rotational torques, generating a signal that can be recorded and used in real-time feedback. And this is a 6 degree of freedom torque, so all your forces in X, Y, Z, as well as your 3 torque components will pitch and yaw. And that's just a depiction of that. So what is the current state of force-torque sensors on the market? So currently there are commercial force-torque sensors. However, these are very complex devices and they require a lot of complex machinery to manufacture. As a result, you can see that these are very expensive and very difficult to acquire. So if you want to use like multiple force-torque sensors, that's not really achievable in certain applications, and these can only be used in one application, for example. So on the left, you have your strain gauges, and these are very high prices, up towards the $7,000, and you start getting towards a little bit cheaper prices. However, these are still very expensive, with this piezo resistive MEMS being $1,226, and as well as this strain gauge being $1,000. This one was specifically from a research article, and it is lower cost, but it's still bulky and requires a lot of machinery. Additionally, we also looked into different force-torque sensors that were a little bit more similar to what our proposed solution was. So all of these are affordable, robust, and easier to manufacture as the previous examples that you saw, but improvements in cost and accessibility can still be made. So for example, on the figure on the left, this is a fiducial force-torque sensor, which utilizes a software to estimate the 3D pose of the fiducials and converting that to a force-torque value. These are still pretty accurate, but this is a little bit more expensive than what we proposed at $50. And there's also another one that we looked into, which was a barometer force-torque sensor, which utilizes MEMS barometers transducers rather than the capacitive sensing, which is what we're doing. And this is also pretty accurate. However, these are a little bit more complex to manufacture in some ways and are a little bit more expensive than our proposed solution.
Okay, so because of this lack of accessible, lightweight, cheap sensor, we decided to make our project CoinFT because it's really inexpensive, easier to manufacture because it consists of 2 PCBs on top of one another. And these PCBs can be very easily manufactured in like standardized factories. And then there's a dielectric squishy thing in the middle that makes the PCBs like twist. So this is what our sensor looks like. And kind of how it works is we take the input force, and with the like squishy dielectric in the middle, we convert that force into like displacement of each of the parts of the 2 plates of the PCB, and that displacement is measured by 2 electrodes that go into a capacitive sensing microcontroller, which then gets sent over serial to an ESP32, which gets sent over Bluetooth to a computer where we do all of our processing. So as you can see, it's really, really cheap compared to all of the other sensors, $1,000 ones, but also the $20 ones. Our sensor with a battery and wireless connection would only be $12 if mass produced. So the PCB design kind of looks like this. So how CoinFT works is it essentially has 4 capacitors on the whole surface of the 2 plates. So there's 4 like mini capacitors on top of the plates. The bottom is ground and the top is the measuring bit. So based on the distances of those like subcapacitors, you can measure that as capacitance, and you can convert the distance back into force and torque. So we can also measure shear to convert a 3 degree of freedom sensor into 6 degrees of freedom, and that works kind of like we just omit 2 of the bottom plate capacitors. We set them as shield. So if this is shield, this is ground, we can have 2 measuring capacitors, and basically when there's a measuring capacitor over ground, that measures capacitance, otherwise it measures shield, and that way we can measure the shift in the top plate. So this is kind of what our design looks like. Our PCB is very simple. It's literally just a capacitive sensor along with our like coil structure. We wanted to keep our PCB as simple as possible and keep the microcontroller or like the wireless connection and processing off board so we can iterate faster. This is kind of what the coil looks like. And then this is the PCB right here. It's a bunch of these plates. There's 8 sensing layers on the front, and then there's 2 on the back that can be set to ground or shield. These overlap with one another. We ordered the PCB as like these 2 lobes that we cut in the middle and then overlap to easily assemble.
So as for the capacitive sensing firmware, it's pretty much just sampling data depending on the mode, processing it, and then publishing that publishing that over serial. So most of the differentiating between normal and shear comes from the processing and a little bit of the sampling. And the sampling, that's where you're able to like do the disabling of certain electrodes to have that topography that Hermione showed before. And then for the processing, it's simply a matter of subtracting to either get the shear, to either get the shear, or for the normal, you just sum them to get like the normal test values. So as for the current state of our capacitive sensing firmware, we did a very rudimentary test to gather the sensitivity, and we're able to detect a change in force from this water bottle here. And we currently have a draft of the firmware so that we can iterate quickly on that. For next steps, obviously the testing of the sensitivity needs to be much more involved. There was some noise that could probably be filtered out. And then there are some questions about if the output to serial is quick enough for application.
So for the dielectrics, we're trying to make a version of CoinFT that is low cost and accessible. Therefore, we're looking for materials that are easy to manufacture and don't involve any of the fancy equipment that people might not have easy access to. To do this, we looked at 2 different main types of silicone. One is a 2-part silicone that you can just mix and then put into a mold. And the second kind is a 1-part silicone adhesive that will just cure when you apply it. And then we did some experiments to just see how this went. So we tried making silicone layers out of the 2-part silicone, and then we were able to make sheets out of that. Then we also looked at the adhesives to see whether those would stick to the PCBs, and they did, and also that they would stick to the other silicone layers. And then finally, we started fabricating for the sensor PCB, so we tried to recreate those layers, but with a little bit more of a precise process so that we can reproduce it more easily later on. And what we found from this is that the 2-part silicone sheets, we're able to make sheets that they don't cure to the PCB, although they are tacky and kind of stick via friction. So if we were to use these, we would probably want another process for curing them so that they can withstand more force. And then for the silicone adhesives, those all did stick very well to the PCBs, so they could serve just as a 1-part dielectric, but they're a lot stiffer than the other materials that we used. For next steps, there are still some things we want to test with these materials, like looking at different methods of adhesion and also evaluating the durability and behavior of the dielectrics, but also given that we have the PCB and sensor, we want to begin putting these dielectrics under test and optimizing what kinds of parameters we need, like looking at how thick or compressible they need to be to work within the range of our sensor and capacitance ratings.
I'll next be going over the data pipeline, which is how our data is transmitted, received, and processed. So starting from the very beginning with our PSOC microcontroller, it's responsible for receiving raw capacitance values from the 4 electrodes on the PCB, C1 through C4. This data is then handed to the ESP transmitter via a 4-pin connector, and this transmitter transmits the data to another ESP32 receiver via ESP-NOW, which is a communication protocol. And this ESP32 receiver is connected to a laptop and is continuously printing these data values to a COM port on our laptops. And And the reason why we chose ESP now is because it was easy to set up and it's easy to use, as well as its low power consumption and low data transmission latency. So how does the data get from our ESP32 to our Python script? As I mentioned earlier, the ESP32 receiver is continuously printing these data values to a COM port on our laptop, and then the Python script takes it from there. It reads in the serial string and then splits it into numerical values and pushes the data into two different types of queues and CSV files depending on whether we are receiving shear or normal. This is our data packet format. It has 5 different parameters, the first being a mode flag. When mode equals 1, we know that the values of C1 through C4 are specifically for shear mode, and when mode equals 0, we know C1 through C4 is for normal mode. We also have a live data visualization. We're using Python matplotlib to plot real-time capacitance values. In the future, we want to create a calibration model and then be able to display calibrated FT values alongside our raw capacitance values. For our next steps, we have 3 main areas. The first is sensor calibration. So we want to be able to convert our received raw capacitance readings into 6 degree of freedom force torque values. And then to do this, we'll need to create a regression model from the instron, which we'll talk about later. Our second is for a real-time visualization, which is where we apply our calibration model to live sensor data in real time, and then, as I mentioned earlier, to display the calibrated force torque sensors alongside the raw capacitance values. In addition, we also want to create a 3D sensor graphic, which is probably more digestible, which shows the arrows on a mock sensor with the arrows for forces and torques. And lastly, we want to send data directly to the PC over Bluetooth, eliminating the need for ESP-NOW and the ESP receiver.
And finally, to wrap up the presentation with the calibration and testing of the sensor, which is necessary to get accurate force and torque values. So as you can see in the bottom depiction in figure 1, it's a 6 degree of freedom sensor that we're making, so that kind of gives you a visualization of what we're trying to go for. However, in order to use an instron, if you're unfamiliar with what that is, it's essentially a material testing device, so it is only uniaxial, so it only goes in one direction. So because of this, it requires certain fixtures. As you can see on the figure 2, this is a depiction of a lap joint. So how we're envisioning this is we would use the fixtures that are already built into the instron, and then we would have the orange fixtures, which are essentially just, you can think of as long roller sticks, and smashing that together to create a state of near shear, which is how we would be able to test the shear on our sensor. Additionally, we would have just a normal, in the bottom depiction, which is just a normal force with the fixture that we would be able to test with our sensor as well. With all of this to say, however, though, if we were to be able to access a actual force torque sensor and also calibrate off of that, that would simplify our process a lot better.
Hit us up.
And that which might seem possible after today's presentation. And that's it.
So you guys said you were taking inspiration from CoinFT. So from what I understood of the CoinFT paper, they were using a stiffer dielectric and using the 127 micrometer tall pillars as a geometric property to achieve their displacement. So you guys said you're simplifying that out to just be a flat layer of dielectric, and how? So without like the with a less stiff dielectric, it won't be able to bond to your PCB. So that's why you guys are using the glue. Does I understand correctly?
Yeah, pretty much the layers that we're using, if you just put them on, they don't like stick to the PCB, and we want them to not come off if you pull it on, if you pull it away. So, yeah, because we're not using any of the fancy equipment, but we do want it to stay.
And it's kind of a goal to simplify the manufacturing process to make it a little bit more accessible, and then also compare our results with the CoinFT paper to see how those results differ in the accuracy levels.
Yeah, we're also not worrying about the dielectric properties of the material as much as the squishy properties and like attachment, even if that like reduces the resolution a little bit, just because ease of manufacturing is our main goal.
I forget your name.
Andre. You guys did the PCB, right?
Yeah.
You know what is floating plate?
Floating plane.
Yeah, like when you have a ground plane that is not attached to the ground.
Yeah.
Okay, that's for design PCB. It's a little bit, it's a concept. You have a floating plate that does nothing, but it is to say that does nothing. For you, if you wanna reprint it, or manufacture, that would avoid having noises due to the ground plane being, like, you have a ground plane, it's not attached to the main ground plane. I'm not finding it.
So yeah, right now we're trying to get like the outside, so the outside layers of the PCB have ground planes, and we're trying to get that. We're seeing how that will affect the capacitance readings, because that's how CoinFT shields their sensor.
Okay.
Like only the inside part is what measures against each other, not the outside. But we'll have to see how it affects the parasitic capacitance.
Yeah, so the PCBs come with a solder mask, right? So
Yeah.
does that like interfere with the electrical permittivity, or is it like negligible?
It hasn't affected, or it doesn't seem to affect the capacitor readings too clearly. Like as you saw before, we were still able to gather like some deltas between like, not applying force and applying force. And I'm assuming that like, when we get like, maybe like start playing around with different dielectrics,